those are nice descriptors that basically, if I say, look at the methylene carbons, you sort of know at that point that I'm not talking about a methyl or a methine. So it's almost like if we were interpreting a map, your eye would be drawn to certain points of that map. So again, the workbook, these physical workbooks that you're actually getting with the bundle, have a lot of problems that will help you to start assimilating that vocabulary to learn in this course. So again, I said morphine was an analgesic. So here is something you may have seen at the doctor's office, a pain assessment tool. 0 is no pain, 10 is the worst possible pain. So does anyone know the symbol of this band, like what band sings this song? So yeah, it's the Rolling Stones, Sister Morphine. It's a great song. Check it out if you haven't listened to it. So again, morphine is an important compound in human health. And so we have a couple more questions, again, regarding the molecule, and the structure is now on the slide here. So in the chat box, how many double bonds, also known as pi bonds, are in the structure of morphine? So based on the chat, it is 4. And again, a double bond is wherever you see a single bond and then a second bond. So this for example, right here, that's a double bond. You have the sigma bond, and then the second line is your pi bond, and that makes it a double bond. So this ring, notice in this ring, how many carbons are in this ring? So there's 6 carbon atoms in that ring. There's 1, 2, 3 double bonds in that ring. That ring itself is a functional group, and it's called benzene. So the benzene ring has 3 double bonds. We have another double bond out here. That double bond is different from all of those. That's called an alkene. Or an olefin. So as we progress through the semester, we're going to learn different bonding patterns of carbon to the other elements in the periodic table. And depending on what those bonding patterns are, those are called functional groups. So we're going to start off learning just hydrocarbons. Those are alkanes, alkenes, and alkynes. Then we'll get into these other things where you see this CO bond here, COH. That's called an alcohol. So we have one type of alcohol here, and then we have another type of alcohol there. So an alkene in the chat here, an alkene is a CC double bond. So we have a nitrogen, that's called an amine. So nitrogen functional groups are called different things than alcohol-containing functional groups. Notice this alcohol or this oxygen here that's in a ring. We have carbon, oxygen, carbon. That is different from an alcohol, and that's called an ether. So part of what we're going to do in the first 2 weeks is learn these different bonding patterns and what those bonding patterns are called in terms of functional groups. say, okay, so the next question is, how many rings do you see in morphine? Again, a ring is basically like a cyclic structure. So I have a little model here. That would be considered a ring. An ether has those elements, COC. So I see a lot of answers of D as in dog or 5. So there are 5 rings in morphine. So we have 1, 2, 3, this is 4, and this is 5. If you still have the structure shown on your phone, I'm going to try to orient it how you see it on the screen here. So if you start moving that around, you can see that this ring I'm highlighting with my mouse, that ring is like flat, but the other 4 rings have a shape. And the reason that is, the carbon atoms in this benzene ring, I know we haven't talked about this yet, but perhaps if you remember from general chemistry or you've done some of the reading already, these carbon atoms, even though they're carbon, they have a different hybridization type. Just by visual inspection, can you write in the chat what hybridization these 6 carbon atoms are? So we have Sp2 versus Sp3. Can anyone explain the difference between Sp2 and Sp3? Aiden has hand up. How do I work the hand? I'm not sure.
So an Sp3 hybridization, the 2s and 2p orbitals hybridize together to share the same energy level. All 3 of the sp orbitals, and in sp2, only 2 of the 2p orbitals hybridize with the 2s.
So yeah, we're taking the atomic orbitals, we're hybridizing them into hybrid orbitals. And again, that's a mathematical process. We are not going to get into that in this course. You do talk about it in physical chemistry if you take that course. So the different atomic orbitals hybridize to essentially, yes, get the same energy level. So is there what do we know about the different bonding patterns between sp3, sp2, and sp? So sp3 is tetrahedral. So what does that mean to have tetrahedral? What type of bonds are present? So remember, we already mentioned so far there's sigma bonds, then there's pi bonds, right? So yeah, I see a couple answers show up. So basically, an sp3 hybridized carbon has 4 sigma bonds. So knowing that, are you going to revise your answer for what type of carbon atoms are in this benzene ring? So I'm looking at the chat. I see sp2 show up. So what is the bonding pattern for an sp2 hybridized carbon then? What types of bonds are involved? So the geometry is trigonal planar. That is correct. That's why that ring looks flat in your structure. Mm-hmm. So let's just visually count here. So let's look at this carbon atom. We know that there's a hydrogen bond here, CH bond. That has to be a sigma bond, right? A single bond, because hydrogen only can bond once. That's a single bond. This is a single bond. That's a single bond. So that's 3 single or sigma bonds. This is a pi bond. So sp2 has 3 sigma plus 1. Oops, sorry. I meant 1 pi bond. So 3 plus 1, that gets you your 4. So what is not shown in this molecule is an sp hybridized carbon. What is the bonding pattern for an sp hybridized carbon? How many sigma bonds? How many pi bonds? So 2 sigma, 2 pi. So that's basically our, yeah, and the geometry is then linear. So when you look at this structure on your phone and you start spinning it around, so again, look at the shape of that ring that contains only sp2 hybridized carbons. It's flat. It's flat because the trigonal planar geometry makes it flat. Then these other rings that have these sp3 hybridized carbons here, that has more of a shape now, a non-planar shape. We have sp2 here; those sort of flatten that ring out a little bit. So when you're looking at a structure, even though it's, you know, lines in letters drawn, you really need to start thinking, what's the hybridization of that carbon? What's the geometry? What's the bond lengths? What's the bond angles? How does it give it that shape? Because this substance, which we said was morphine, you pop a pill. If you have pain, that pain is relieved. If you think about that, we won't talk too much about it in this class, but think about the complexity of what's going on. When you take that pill and it goes down your gut and it's being metabolized, it's then distributed to over your body, and it's basically dulling the pain. So this collection of carbon, hydrogen, oxygen, and nitrogen is a pain reliever. And that's pretty wild to think about, because, for example, if this OH group wasn't here, that's a different molecule. And does that molecule have the same pain relieving properties? We don't know. So the shape of the molecule, is very important for interacting with enzyme drug sites within your body. So let's go to the next question. How many carbon atoms are in morphine? So yes, basically, pain relievers will hit some sort of receptor, you know, wherever that receptor is located. So the molecule has a shape, the receptor has a shape, they dock together, and then that relieves the pain signal. So I see a lot of C's and D's. I believe the answer is D, it's 17. So when you're the easiest way to do this, in my opinion, is just to draw the molecule out and just start counting them. Put a number by them. You know, 1, 2. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So why do I bring this sort of stuff up? Again, you really want to get very good at these very straightforward activities. So there's 17 carbon atoms. 17 times 12 is some number, and that's the contribution of carbon to the molecular weight of that compound. How many hydrogen atoms do you see? So Christina put 204 is the 204 is the carbon contribution to the molecular weight of that compound. So Bailey put 19 hydrogen atoms. That's what I got as well. So 19 times 1 is 19. That's the hydrogen atom contribution to the molecular weight. Nitrogen is 14. Oxygen is 16. So 16 times 3. I think that's 48. So that's basically the contribution of each element to that molecular weight. So with the mouse, I'm going to point those hydrogens out. There's 3 right here. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Again, other than this carbon right here, we have a carbon. We see 1, 2, 3 bonds. We know that carbon has to have 4. So the implicit hydrogen is not shown, but it's there. Is the mouse still frozen? Okay, so we have about 20 minutes left. I want to run through a couple more slides because recently I saw a news article. So yes, for a carbon atom, if you do not see 4 explicit bonds, then the remaining bonds belong to CH bonds. So I want to show 3 more slides on opioids. This has been sort of a hot topic over the past couple years because of this company right here, Purdue Pharma, which produces OxyContin. So I've taken oxycodone or OxyContin for a surgery that I've had. And so I took a pill. I went to the bathroom. I'm standing there taking a piss. The next thing I know, I'm in the bathtub. I mean, I was knocked out. So I passed out from taking 1 pill of this. And I said, okay, that's good for me. Give me something else. So it's a pretty potent analgesic, but it is not the most potent analgesic. And so the reason I bring this up is because Purdue Pharma is basically being sued by the state's attorney generals, and they're seeking a lot of money. So $2.2 trillion. Can you imagine that? The federal government budget, I think, is like $1 trillion or something. So there's no way Purdue Pharma has $1 trillion. But what this shows is that this molecule is so addictive that, you know, it's been overprescribed and people get addicted to it, and it's caused a lot of health issues, and basically is, you and I as taxpayers, we're responsible for taking care of people that are addicted to either prescribed drugs or illegal drugs. So Purdue Pharma had some marketing practices where they were illegally marketing this, and they were marketing it, you know, off-label, as they say. So I said it's not the most potent analgesic. So here are some that you've probably heard of in the news. And I have down here this word equianalgesic. And the red numbers that you see are basically relative to morphine. Again, morphine is extracted from a plant. So it's a natural product, as they say. Hydrocodone is a synthetic molecule. So hydrocodone, it doesn't come from a plant. It doesn't grow on a tree. It's not produced by an animal. It's not stripped out of a mine anywhere. I want you to focus your eyes on morphine and on hydrocodone. In the chat box, can you tell me any differences you see between those two structures? So Bailey says there's an OCH3 group. So if we look up here, OH, we have OCH3.
Okay.
So why am I showing you this? Remember I said this functional group here, OH, that's called an alcohol, right?
Mm-hmm.
Now we're removing this H, and we're replacing it or substituting it with CH3. That's now a different functional group. This alcohol has been transformed into an ether. We also have here, if you notice, see this OH group? We have a sigma bond. Now we have a double bond. That's a different functional group. So by making those transformations, notice this number stays pretty much the same. Those are equally potent molecules. Codeine is 1/10 the potency. And what has changed in codeine? We're keeping this alcohol group the same, but we're putting in this group here. So this structure here, what does this dotted line mean? Again, we'll talk about the thicknesses of these lines as we go through this course, but what it means, it's basically projected behind the screen. This wedge line, this bold line means it's coming out, this ring is coming out towards you. So look at morphine versus OxyContin. What sort of differences do you see now? So see this sigma bond? See this OH group? That H goes away. Now you have a pi bond. See this H right here? That's substituted. Now you have OH. This OH becomes CH3O. So by doing these substitutions, look what you've done. You've increased the potency of morphine. So think about why that would be important. You know, if you have, say there's a soldier that has a major traumatic injury from war, and morphine just ain't cutting it. You need more potent medicines, and that's what has done through transforming these functional groups. So Dilaudid, and then everyone's heard of heroin. Heroin's a little bit more common. So what is heroin? Look at this number 5. It's 5 times as potent as morphine. The major difference is if you look at this OH group here and this one here, we've now put a different functional group on. So heroin is essentially the morphine skeleton with these 2 functional groups. So one of the societal issues is that why do people become addicted to heroin? It's not because they like to have a good time. It's essentially because if they've had an injury and they've been prescribed oxycodone, your physician can only prescribe so much of that due to the laws. At some point, the physician is going to say, I cannot prescribe anymore. However, the patient is now addicted to this, and it is extremely physically difficult to outrun addiction. So what happens? Heroin is easy to get because it's available illegally. So people turn to heroin, and at that point, you're sort of screwed because from what I understand, heroin, you take it once and it's like flipping a switch. You're just addicted. So why is this? Look at this structure here, dopamine. See this ring that I'm highlighting? And I highlight this ring here. That's sort of, this ring maps onto that ring. You see this oxygen, that oxygen, this oxygen, that oxygen. Then we can trace down to this nitrogen. So we have this group, then nitrogen. So dopamine exists in your brain. It's a neurotransmitter. So what these opioids do is they're interacting with the same receptors that the dopamine interacts with. And they just so happen to hit that receptor more than dopamine, and that's what causes addiction. So Narcan has been developed as basically an opioid antagonist. Does anyone know what the word antagonist means? So yeah, it works against. So basically what it's going to do, when this is administered, it's going to displace any of these other opioids that are already existing in that receptor. However, it does not have the same potency in the sense of addiction. So these last 3 are all synthetic compounds. They're not derived from the morphine skeleton, but look at the numbers in red. U47700 is 10. Everyone's heard of fentanyl, I would assume. It's 50. Look at this bad boy, carfentanyl, 10,000. 10,000 times more potent than morphine. So how is fentanyl different from carfentanyl? Look at this hydrogen right here. We've substituted that for a different collection of atoms. That's a different functional group. Just by doing that, look at how much you increase the potency from 50 to 10,000. So why does fentanyl kill people? So I'm a big fan of Forged in Fire. That's Doug Marcada. So how much fentanyl can kill you? In this vial right here, that's the amount of pure heroin that can kill you. The vial to the right is the amount of fentanyl. So you can see you could probably count these specks. So 1, 2, 3, blah, blah, blah. And there it is, these specks laid next to a penny. And look at it in relation to that date. If you kind of have an idea about how big that date is printed, that's not much fentanyl. And so why can this stuff kill you? Because basically, if you're addicted to heroin, people have started cutting heroin with fentanyl. And you know, if you're not making the proportions right, you can get a hot shot and die, as they say. So what I would like to do now is transition to another type of activity in the last couple minutes. And this is called Think, Pair, Share. We would do this in class, you would get with a partner, but obviously you'll have to do it sort of alone. We'll use the chat function. Let me see if my other camera works. No, it's still showing the inverted image. So I'm going to have to figure that out. So otherwise we would have done some problems in here. So like Phil Hartman, I don't understand this technology. I'll have to figure it out. But let's go ahead and spend the last couple minutes doing this Think, Pair, Share. So knowing what you know about carbon and hydrogen bonding, if you're given a molecular formula C3H8, draw a reasonable structure that obeys Lewis dot rules. So why don't you draw a structure down, and if you're willing, you know, you can show that structure to your webcam, and depending on how many people you can see, I only see like 2 people now. Maybe you can hold your structure up to the webcam. So Rosemary, I see yours. What might be a problem with your proposed structure?
It accounts for both resonance structures. But let's see. Actually.
So Taka, if I'm pronouncing that correctly, yours is correct. So Rosemary, how many carbon atoms have you drawn? in your structure. Okay, so 6. So again, I think every sort of opportunity is a learning opportunity. So if we're considering what the prompt is, again, I'll use this term quite a bit, metacognition. So I see Aiden, that looks correct to me, Aiden structure as well. So if you're considering the prompt is C3H8, your structure should only have 3 carbons, 8 hydrogens. So again, it's sort of a double check. So Jalen's looks correct. Sydney's is correct. So we see by drawing this structure, carbon can have 4 bonds, hydrogen has 1. So Blakely, you should be able, do you guys see other people on your, do you see anyone else? So I see 6 people now. David's looks correct. No one sees anyone else. That's interesting. Let me, so Bria says you have to click on their name. Does that work? Jalen, I see a little bit of glare. Maybe if you tilt it down a little bit. Yeah, that looks correct now. James Hinson's looks correct. Rosemary's looks correct. Ashley, that looks good. Camille's, that's correct. So Sarah Mitchell's, that looks correct as well. So Sarah also has the next sort of prompt. So how many unique carbons does the molecule have? How many unique sets of hydrogens and the ratios? Can you see each other now, or is that, again, I don't know like how your systems look. Maybe we'll start a Canvas discussion to figure out how you guys can see each other, because I'm not sure how to change that on my end if I can. Yeah, I'll have to get back to you on that. So the other thing in the last couple minutes, if you're looking at that structure, if you're looking at your structure, you have CH3 groups, you have 2 CH3 groups, and you have 1 CH2 group, right? So the terminal CH3 groups are the same type of group. So that's 1 unique type of carbon. Then the middle CH2 group is a different type. So that gives you 2 types of carbon. Then the same thing for the hydrogens. The CH3 groups are the same. Then the CH2 group is obviously different, right? Because it's not CH3. So we have 2 unique type of carbon, 2 unique type of hydrogen. And the ratio, what is the ratio of the hydrogen types? So it looks like if you click on someone's video, you should be able to see everyone, other people's cameras, possibly. So Blakely says 2 to 1, which is correct. So 6 to 2 is correct. So if we take 6 to 2 and divide it by 2, we get 3 to 1. So what that means is we have the methyl groups, which are 3 apiece, so that's 6. Then the CH2 group is 2, so the ratio 6 to 2 or 3 to 1. And so the reason I bring up that thought exercise is because conceptually that is the foundation for spectroscopy. We are going to be learning a lot of chemical reactions over the course of Organic 1 and 2. A reaction produces a product. How do we know what that product is? Because just because we write something down doesn't mean that nature's going to produce that product. We have to use spectroscopy to verify that. So what you've just done with this uniqueness test is the conceptual understanding of NMR spectroscopy. So we're about wrapped up for today, but go ahead and watch the lecture video, start doing the Wiley Plus homework, and if you have these workbooks, start marking them up and doing the problems. I'll try to get this document cam figured out so we can do some of those in the next chat. But basically, the way this is going to work, these chat sessions, because they are not mandatory you attend, we're basically just going to work on like stuff we did today. And then you will see links in Canvas for actual more formal lecture things. So if you go in the module, you click those YouTube links, those are the lecture materials. So I'm going to go ahead and close down this chat for now. If you have questions, shoot me an email. And again, I'll try to get back to you within a reasonable amount of time. But other than that, stay safe out there, and we'll see you Friday.